Okay, we're going to talk about the washer method for finding the volume of solids of revolution. So this orange shape here is what we would call a washer. It's basically just a circle cut out from another circle. So in order to understand volume, we've got to think about the area of the washer first. So if you think about this for a second, the area of the big circle is going to be pi times 13 squared, and then we have to subtract the part that got cut out, which would be pi times 8 squared. Well, I don't even care what the answer is. I just want to make sure that we understand the idea here that the area of a washer is pi times the bigger radius minus pi times, well, I said that wrong, pi times the big radius squared minus pi times the little radius squared. And if I want to get fancy, which I do, I can factor out the pi and get that. So we're going to use this formula here. Now that's the area of a washer, and really I want to talk about volume here, but here's why. The volume of basically anything is the area of its cross section. In other words, if you have some kind of thing and you slice it up, those are cross sections. And so whatever the area is of those cross sections, for example, if you had a cylinder and you took that cylinder and you slice, you would get a bunch of circles. Think of like a roll of quarters all stacked together. You would get a bunch of circles. And so the volume of that is equal to the area of the cross section times its thickness. Or in other words, if you find the area of the circle, pi r squared, and then somehow account for the thickness of the stack, then that will give you the volume. So that's why when we do the disk method in calculus, that's why the formula looks like this. Pi r squared is the area of the cross section, because disks look like circles, and then we account for the thickness by using dx or dy. So when we do the washer method, in other words, if we slice the volume up and we see washers instead of this, then we're going to follow this formula instead. So this is going to be the formula that we use. Now some good news for you, because this can get a little tricky, you'll see from the example. Sometimes it's sort of hard. You're like, well, what's the big radius here? What's the little radius? Well, the good news is if it's a dx problem, the big radius will be the top of the shaded region, and the little radius will be the bottom of the shaded region. Wow, I totally messed up my color coding there. Must be green. And if the problem turns out to be a dy problem, it's awesome because the big radius will basically be the right side and the small radius will be the left. Now there's going to be some exceptions for this when we move on to some other types of problems, but for washer problems where we revolve around the x-axis or the y-axis, this is how it's going to be. In fact, we might as well just get this right on here. If it goes around the x-axis, we use dx, and if it goes around the y-axis, we use dy. Alright, so let's take a look at this and see if this makes any sense. So here is a problem. Find the volume if the region is rotated around the y-axis. So here's this shaded region. We've got a couple curves here. We got y equals x squared, and then it some sort of just cuts off at 1, 1. And then we've got y equals the square root of x up here. And so what we want to do is try to envision this thing. If I rotate this around the y-axis, what is it going to look like? And the answer is it's going to look something like this. If I start revolving around the y-axis, I'm basically going to just trace out the shape of a bowl. I've got that region, and that region there is sort of going to be like the thickness of the bowl. So here it goes again, and it's starting to work itself around. It's rotating. It's went behind the y-axis. Now it's coming around the left side of the y-axis. Here it's going to go in front of it, and I'm going to get this big bowl shape. And so if I start slicing this baby up, what I'm going to see is something that looks like this green section. I don't have the whole bowl here, but you know, if I did, you know, here it is, and here's the bowl. And if I chop, 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 I'm going to get a bunch of rings that look like this green section. Well, those green sections are washers. And so um, what this leads us to is a really important idea. I mean, what makes this a washer is the fact that there's empty space in the middle. And so any problem where there is empty space, no, I don't want that model, I want this one. Any problem where there is empty space between the region and the axis you're revolving around, it's going to be a washer. If this space was filled in, if this was all purple somehow, you know, different graph or whatever, if this was all purple and we're going around the y-axis, it'd be a disk because it'd be rock solid. There wouldn't be any empty space in the middle to get washers. Now if I go around the x-axis, it would still be washers. So that's an important thing, that if I see empty space in there, it's going to be a washer. And so what I want to do is just apply my washer formula. This one goes around the y-axis, so it's going to be a dy problem. And what I've got to do is I've got to work out what the big radius is, squared, and what the little radius is, squared. Since this is a dy problem, I'm going to do right minus left. So the right side of this thing is this curve, which is really the same thing as x equals the square root of y. And the left side of this region is this green curve, which is really going to be x equals y squared. I'm just converting there. The washers, remember, the washers would be going this way. The washers are stacked up from 0 up until 1. That's it. I graph that thing, I solve it, piece of cake. Now let's change this real quick, since we've got another minute or so, or maybe a couple minutes, and let's just see, would it make a big difference if I was going around the x-axis? And the answer is no, it really wouldn't make a big difference. It actually gave almost pretty much the same exact shape. It's just being tipped over on its side. But it's definitely still going to be a washer problem again. So if we switch this and say, oh, okay, what would I do if I went around the x-axis? Well, then I don't have a model for this one, but I can sort of draw it. If I revolved around the x-axis, I'd get that bowl shape. But because of this empty space in here, it's going to be hollowed out. There's going to be a hole. And so that makes this another washer problem. And so that means I find the big radius and the little radius. And it's dx because I'm going around the x-axis. And so what I've got to find here is what is the top of the shaded region and what is the bottom. And so the top of the shaded region is y equals the square root of x. Otherwise there'd be a pi out in front of this. And the bottom of the shaded region is y equals x squared. And now the washers this time are going this way. And so they're stacked up starting at 0 and ending at 1. And then I go ahead and, you know, this one I could do by hand if I really wanted to, or I can just graph it on my calculator. Remember, discs, if there's no space between the shaded area and the axis that you're revolving around, washers if there's a space in there.